Hello everyone. In this session, we will be discussing about how we can use the concept of random forests for classification purposes. So we know that as a part of supervised learning, there are two major aspects. One is the classification problems, one is numerical prediction problems, which in other way come under the category of regression problems. Within this classification, again we have some broad categories of classification where you have binary categories where we are talking about two categories only, like the examples of whether the person has a diabetes or does not have diabetes. So they are like binary classification. We have examples of multi-category classification which I am taking up in this session, and we could also have something like ordinal classification. So all these are different kinds of classifications. So in this session, we are primarily looking at how we can use the random forests for multi-category classifications. Later on, I will be taking the examples of how we can use them for binary classification as well. And similarly, we can use random forests even for the regression purpose as well. So we would be talking about all those things in the upcoming sessions. But this session is more targeted towards how I can really use the random forest for multi-category classifications and how it can very well result in improving, or I really need to check whether it will improve the prediction purpose, the prediction process for a set of data. So in this context, for the purpose of this session, I would like to look at three major algorithms along with their implementation in R. For the same data set, I'll take one single data set. This data set is relating to vehicles. Based on the various attributes of the vehicle, they are classified into three groups. Right, so there is a classification of bus. Some of the vehicles are classified as van and some of them are classified as SAP. So, and there are different attributes regarding the compactness of the vehicle, right, or regarding the elongatedness of the vehicle. So like that, we could see that regarding the hollowness, the radius, etc., different variables that are associated with the particular vehicle. We are trying to see whether you can classify that particular vehicle as a bus or a van or a SAP. And I can use decision trees for this purpose because decision trees are also useful for multi-category classifications. Or I could have used the support vector machines for this purpose. I could have used neural networks for this purpose. I could have used almost any kind of techniques for executing the same kind of a business situation. Now, I want to look at the usage of random forests and especially three major algorithms. One is the classification random forest, which actually comes from the package itself called as random forest and the function itself called random forest. So the basic implementation of the random forest comes from here. Then we are also talking about the conditional inference classification random forest, and we will also see the usage of random ferns for the same problem. So how are the random forests versus random ferns yielding the results for the same kind of a business problem, right? So here let me quickly look at the data which can help you to understand a little bit. So this is the vehicle related data that I am loading, right, which is the CSV file is there in my folder and I am loading the CSV file from that particular folder. Let me look at the size of this data. The size of this data is 634 rows are there and 15 columns are there in this particular data. Looking at the summary, just to get a basic understanding of the same. So there is the compactness for each of the vehicles, probably the class. We are talking about three different classes. The bus, there are 218 vehicles falling under the category bus, 217 falling under Saab and 199 into the van. So this is the overall set of data that I am having. So 435, 634 records altogether, out of which there are 218 buses, 217 SAPs and 199 vans. So this is how the compactness is changing from 78 to 119. The circularity from 33 to 58, these are all the technical terms which are associated for the classification of the vehicles. The distance circularity from 40 to 112, the radius ratio ranging from 104 to 333. So I want to see, based on these various attributes, can I really identify if some particular vehicle will be a bus or a SAP or a van. Elongatedness ranging from 26 to 61, the maximum length rectangularity ranging from 118 to 177. So I could see that these are some of the various aspects associated with the vehicle, and we are trying to see, using the random forest, if we can really identify what kind of qualities, what kind of attributes can be associated with a bus, what type of attributes will be associated with a Saab and a van. That's the major intention in the process. So we will use all the three algorithms for the same data. Probably we'll create a training data and a testing data, again with the same subset. The same subset will be used for training all the three algorithms, and the same subset would be used for testing all the three algorithms, so that we can really assess which one has done better compared to the other in terms of classifying this multiple category data. Alright, so let's get into it. Initially, let's get started with classification random forests, which is implemented through a package called random forest, and it has a function also called random forest. So let's look at that part. First, let's have an installation of the packages. The random forest package. So I'm installing the random forest package. Okay, the package is installed, random forest. Let's load the package as well. Once the random forest package is loaded, the thing that we are looking at here is we are using a function called random forest, wherein we are talking of some important aspects. But before, instead of looking at this entire aspect, let's directly question the random forest itself. So questioning the random forest gives us the help regarding the function random forest. So here you could see random forest implements Bryman's random forest algorithm. So again, when you are going more technically, yes, you have to understand what this Bryman's random forest algorithm is. But here we are getting an implementation of that algorithm, which means from a business perspective, I can quite comfortably use random forest, and I can do the classification of the data more effectively. And this Bryman's random forest algorithm is used both for classification as well as regression, which means when we touch base regression at a later point in our upcoming sessions, we are going to reuse this random forest package again. It can be used in unsupervised mode also for accessing the proximities among the data points. That's one more advantage of using random forest, not just in supervised learning. It can very well be used in the unsupervised learning mode also, just to understand the proximities. How is the closeness between the various data points, or what is the level of distance that is existing between the various data points. Now, if you look at the way the random forests are being taken, the first thing I have to give is a formula. Whenever I am talking about a formula, I have a response variable, tilde, all the explanatory variables. So we have, in our case, the response variable would be our training data, response variable would be our class column, whereas the explanatory variables would be the set of all the other variables. So I can very well use a dot for it. Then the data, we have to specify the training data with which this tree is learning. Then a few attributes that are coming from here. Some of the important attributes, if you see here, entry. Entry is typically talking about the number of trees to grow. This should not be too small a number. This should not be set to too small a number to ensure that every input row gets predicted at least a few times. So here it's better if your size of the sample is much larger, it's better to go with a much higher size of the tree so that each observation can get predicted at least a few times. The default is 500, but if you want to make it 1000 or something, you can very well go ahead with that. And apart from that, you can also talk about the mtry. Mtry is a very important variable out here. The default implementation is there is a square root of number of columns of x. So if I am talking about the number of columns, here in our case there are 14 columns. So square root of the 14 and on the floor side of it, which is the downward side of it. So if we are talking about the factors, then it takes the floor of n col by 3. So it will take the number of columns by 3 and it will typically take the floor of it. That's the default mtry. Mtry is nothing but number of variables. We have already discussed when we have talked the conceptual aspect that if there are 14 attributes, it will take randomly a small subset of attributes. So that is what is being specified as mtry. So out of the 14 attributes, it can take 4 of them randomly, some 4 out of the 14, and based on that 4, it can actually build a tree. Then it will take some other set of 4 and again build another tree. Then randomly again it takes another set of 4 and builds one more tree. So this is what goes as a part of mtry. Number of variables randomly sampled as candidates at each split. So how many variables you want? 3, 4, 5. So the default values for classification, you see square root of p, which is the number of variables in x, and regression, it would be p by 3. So typically around, in fact there are 14 variables, the default would be around 4 or something. So that is the mtry, but if you want to change the mtry, saying that you want to try out with 3 variables at a time or 5 variables at a time instead of 4 which is coming by default, you can very well specify your mtry. But if I am simply omitting it, it means it will take the default implementation of the same. Right? In case of classification, it will take square root of p which is square root of 14, and we are talking about the floor of that. Floor is the downside. Square root of 14 is coming out to 3 point something, so it will take 3 variables at a time in terms of the implementation for classification purpose, and in case of regression it can take 4 because 14 by 3. So for when we are talking about the regression, it will take 14 by 3, which is approximately 4 variables at a time out of the 14. Randomly it picks up 4 variables out of the 14 to build the model, to build the trees, whereas in case of classification it can take square root of 14, which is close to 3, which would be used for building the tree. So otherwise, if I want some other numbers, then I can replace the m trie with my own set of numbers. Then the sample size, right? If I want to set the sample size in this case is the size of samples to draw. For classification, if sample size is a vector of the length of number of strata, then sampling is stratified by the strata, and elements of the sample size indicate the number of draws from the strata. So either you can specify the sample size. So if we are talking about if n row, if the replacement of n row L ceiling of 0.632, which is approximately 2/3 of the n row. Number of rows, it will take approximately the 2/3 of the number of rows. So that's a kind of typical sample size it takes by default. So we can very well leave the sample size to the default. All these things can be set to default. But importance, I should not set it to false. I'll set it to true in all cases. So because it will assess the importance of the predictors. Out of those 14, which one is more important in terms of classification into bus, van, SAF, which ones are least important. So I'm going to get an understanding regarding the importance when I'm setting it to true. So that's the reason I'll set the importance to true. All others I can leave them off. Proximity. One more important variable. Proximity, if you see, should proximity measure among the rows be calculated? I'm really interested in seeing which of these observations are close by to each other. So this is what is giving me the proximity. So basically, even for unsupervised learning, this proximity plays a very important role. So I can very well showcase that I want to go ahead with the proximity part as well. So that's how we are applying this random forest function. Let's load the data. Let's then implement the function altogether so that we'll get a clarity on the process. So we have loaded the random forest package. Get the necessary data. We have already got that. Right? We got the necessary data. We will have to split that into the training data versus testing data. Right, we have to split this whole data into a training data and a testing data. So let me split that. First, the data wise we have checked there are no NAs in it. We have looked at almost all the aspects of the data. So we'll split it into training data and testing data. Overall we had 634 rows. So let me understand the 70% of that 634, which I want to keep it as a part of the training data. So approximately 444, I'll keep it as a training data. So based on that, I'm creating a variable called train. So first let me set a seed so that I'll set it at 1000. Then I'm taking a variable called train, which will be a kind of a random sampling between the numbers 1 to 634. I am going to pull up some 444 observations where there is no replacement. Replace equal to false. So that's where this would be a part of the train. And if I quickly look at train, obviously there are 444 values that are selected between 1 and 634 in such a way that there is no duplication across in the process. There is no duplication across. Now, based on this set, we want to create a training data which is a subset of vehicle, which will take only those rows which are there as a part of the train, but it will consider all the columns. Similarly, I have a testing data which again is a subset of the vehicle, which will not include those rows that are there as a part of the train. It will include all the columns. So that's how I am getting my training data as well as my testing data. So I have split the training data and the testing data. I have to really first understand how many trees I want to build, right? So I have to specify num.trees, which talks about how many trees that I have to, or probably I have entry, right? Not num.trees. So here I have to give it as entry, sorry. Entries I have to set what should be the value, how many trees I want to build in the process. Let's set it to some 1000 or something. Split the data into training and testing, which we have already done. Now we are ready to build the model. So we can estimate the random forest using the training sample, and we are using the function random forest. So as I have already given to you, we are fitting a preliminary random forest, right? So let's fit the initial version of the random forest. So I'm calling it as fit. I'm using the function random forest. Then our dependent variable or our response variable, it's better that I check out for the names of the variables. So let me just check the names of the train data so that I can type them more comfortably. Now let's do the fitment. We have a function called random forest. The dependent the dependent variable is class tilde. Then I have independent variables which I can consider with a dot, which means all the other variables would be included as a part of my independent variables. The data in this case I can very well set it as train data. So the whole data is going as a part of the training data. Then look at what are the other variables that I have to give. Data I have given. Then I have to provide the entry. By default it is 500, but let me just set this to 1000 so that all possibilities will be taken care of. Then mtry, I will by default leave it to the default. Even the sample size I will leave it to default, right? It will take around 2/3 of the number of rows, which is very clear. So I will leave it to the default. All other things I will leave it to default. The only thing is I will set importance equal to true. Now this is where I can change the number of trees, and based on that different models can be tried out. So the importance I will set it to true. Proximity also I will set it to true in this case, so that it will compute the distances also for me quite comfortably. Now these are some of the things I want to use as a part of the model. So based on this I have fitted. So let me save this so that if I want to change the model at a later point, probably just by changing this in the small code, it should simplify my repeated performance of the code. So we have fitted a model out here. Then I can very well look at what is there as a part of the fit. So let me try this. Okay, now if you see, if I'm just typing the name of the model, it first gives me the formula that I have used. So this is the formula that I have used. I went for number of trees, 1000, number of variables tried at each split, right? This is the classification purpose, this is the classification data. So you could see that it has taken the square root of 14 and the floor of it, which means it has tried 3 variables at each split. The out of the bag error estimate, the error rate is only 6.08 from the training data. This is an error rate with respect to only the training data. This error rate is coming out to only 6.08%. And look at the confusion matrix, the classification. There are, so this is the prediction part, this is the actuals. You could clearly see here 143 buses are correctly classified, but 2 of them are classified as sub and 2 of them are classified as van. So for the bus, the class error is hardly around 2.7%. Whereas in case of sub, 129 are correctly classified, but 8 of them are being classified as bus and 14 of them have been wrongly classified as van. So the 22 of them have been wrongly classified, resulting in a 14.5% error for the classification of sub. And when it comes to van, probably it looked like 145 of them are correctly classified, only one of it is being wrongly classified as a sub, resulting in an overall class error of only hardly 0.6%. So, which is very clear for us that Saab is slightly having a difficulty in terms of learning, whereas the bus and the van, they were much better in terms of the classification part. So the overall, we are getting the confusion matrix as well as the out of the bag estimate for this particular random forest. Now this thing I could have got just by typing the name, or I could have used the print function also. Print also is giving me the same solution, right? Both of them are leading me to the same solution here. So you could clearly see the information that we have got. We have already set the proximity and importance, both of them, to true. So we will see how we can retrieve that information. The print function has given us the details regarding the random forest. The major details that we have got is the out of the bag estimate of the error rate. So on the training data, the estimate of the error is hardly around 6.08%. Number of variables that came out at each split is 3. So M try, now if you want, you can very well change the M try from 3, you can change to 4, 5 and see if there is any kind of an improvement in the estimate. So this is where I talk about creating different models. Let's say I want fit 4 model, right? I want fit 4 model. What is that I'll do? I'll repeat the same process, but I will set M try equal to 4. Rest all I'll keep it as it is. And I'll see if there is any kind of an improvement in the OOB estimate. Because when it is 3, this is how the mechanism came out. Now I really want to check if 4 variables are being taken randomly, is there any kind of an improvisation? The OOB error rate is still 6.08 itself, and you could see that there are small differences in the class errors. Bus wise, there are only 3 misclassifications, whereas here we had 4 misclassifications. Whereas in case of Saab, it is 7 and 15, still 22, resulting in the same 14.5%. Whereas in case of van, instead of 0 and 1, it became 1 and 1. So some kind of misclassification cropped up in case of van rather than the bus. So fit 4 was also giving me more or less the same kind of an error, out of the bag error. So I may have to now try on my testing data, but when I am trying it on the training data, even fit 5, wherein I am asking it to take 5 variables at a time. Now here also the error rate is this much itself, Whereas what we could see is when we are going with 5, here it is 1 and 2, whereas here it looks like slightly an increase in the error, only 128 are correctly classified, whereas in case of van again it's 145 that are correctly classified. So you could see that when you are going with 3 variables at a time or 4 or 5, overall out of the bag error estimate is to the extent of 6.08% itself. So on the training data, even if I am going with these 3 or 4 or 5 different kinds of 5 variables at a time, all of them are giving us more or less the similar kind of out of the bag error estimate. So the number of variables tried at each split, we got it as 3 by default, but we tried out the 4 as well as 5. We have looked at the confusion matrix. For each class, what are the errors? So which class is very appropriately predicted, which class is becoming more and more erroneous in terms of prediction, and along with that we are also looked at the out of the bag error estimate with respect to the training data, which is around 6.08%. The error is much smaller, which could be an indication of overfitting as well. There is a lot of overlearning that might have been done by the data, which we might have to sort it out. We might have to see whether the same kind of an accuracy is coming out on the test data. If it is coming, then probably we have a model in place to predict what kind of vehicle it is just by looking at some of the attributes of that vehicle. I can really have a look at the visualization of the error rate by iterations. As the iterations are increasing, how the error rates are typically changing. And I can use the plot function for that, where the error rates can quite comfortably be visualized for each category along with the overall out of the bag error. So I can simply go with plot of fit. So this is how the errors have been changing. You could clearly see here the misclassification wise. This is an overall out of the bag. The black one indicates the overall out of the bag error. Probably initially the error is much higher, but after a certain point the error has stabled out in the range of 6. So we are more interested in looking where the stabling out of the error is typically happening. So as the number of trees is increased 200, 400, we see that the overall out of the bag error estimate has almost stabled out. Even if you look at the blue one, which is on the lowest side, which we are easily able to identify it to, which we are able to identify it to van. So the van is looking stable after 200, 250 or 300 observations, right? Even after 150 observations, we see that the error is more or less stabled out. Even in case of bus, the error got stabled out after a certain point. Whereas in case of Saab, we see slightly a volatile kind of stuff up to 500, but after that there is a lot of stabling out of the observation. So this kind of graph, this kind of plot helps us in terms of understanding the visualization of the error rate and how many trees are more or less necessary for us to get the least possible error altogether. So this plotting has really given us some kind of insight into what is the minimum number of trees that I need to try so that the error rate is more and more stable in the process, right? Now, now that we have seen the error rates more or less stabilizing after 300, 400 trees, the other thing that I would like to look at on this data is the cross validation. I can create an n-fold cross validation, right? Probably in general, we generally look at a 10-fold cross validation. So I can very well perform a 10-fold cross validation to really understand with respect, how many predictors are typically more and more important, right? I really want to assess out of the 14 predictors that I have, how many of them are really very, very important for me. So I'm doing just we already know that the tenfold cross validation is more for assessment of the robustness of the model. So we can use this function called RFCV, wherein we have to specify. We will look at RFCV first to see how we need to give the data to it. RFCV in case of random forest, it is showing the cross-validated prediction performance of the model. So depending on what fold that we are putting, generally we will put a 10-fold. It shows the cross-validated prediction performance of the model with sequentially reduced number of predictors. So if I have only 3 predictors, so basically it looks like this. So there are overall 14 predictors, right? Now it understands the importance of each of these predictors, and based on the importance that is associated with the predictors, it goes ahead with a sequentially reduced number of predictors to see what could be the minimum number of predictors that I can go with, or is there a scenario where by adding more and more predictors is the error actually coming down or not. So it's basically trying to assess whether the predictors that we are using as a part of the model are really required, are really having some level of importance or not. So that is what would be typically assessed as a part of this cross validation. And we could see that it takes train X, which is a matrix or a data frame containing the columns of the predictor variables. So we require the columns of predictor variables. Train Y is the vector of response, must have length equal to the number of rows in train X. So we are separating the training data into the attributes separately going as train X, and the response variable separately going as train Y. By default, cv.fold is 5 number of folds in the cross validation, but we can very well set it equal to 10, and I think all other things we can very well keep them. The other argument that whatever you have passed on to the random forest, you have to pass those things out here, right? So we can give the entry, which is the number of trees, and I also need to give whether this process is recursive. When I am saying it is recursive, the variable importance is reassessed at each step of variable reduction. So basically one variable is removed, and after the removal of that variable, again a recalculation of the importance of all the variables is typically performed when you are saying recursive equal to true. So in this case I will leave the mtry to 3 itself, which is the default one, but I can very well try the 4 as well as 5 also. Because we have tried our base model with those things, I can think of trying it even with the n-fold cross validation as well. So let me do that n-fold cross validation. Let me call it as CV, where I am using RFCV as a function. My train X is from the train data. I am taking all the rows, but I am not considering the 15th column. That is what is my train X. Whereas train Y is again from the train data. I am considering all the rows but only the 15th column, which is what is my class related column. Then I am setting my cv.fold by default, which was 5. Let's say I'll set it to 10 because I am doing a 10-fold cross validation. right? It is doing a sequentially reduced number of attributes based on the ranking of variable importance, and it is using a nested cross validation procedure. And I am more interested in looking at the minimum value of the cross validation error, and based on that I will select what are the optimal number of attributes or the predictors for this model. Do I need to use all 14 of them or is it okay if I am going ahead with only choosing 10 different predictors rather than all 14? So we are doing a cross validation. Entry, I will set it to the same 1000. Mtry, I will leave it to the default, so that's the reason I don't want to put that here. And I also can give the recursive equal to true, so that the importance of the variables are recomputed after every removal of the single variable from the model. So there is a cross validation that is performed, and this cross validation I really want to look at for each number of variables. We can see for each number of variables, so I can say with CV I am more interested in looking at the plot that is between the number of variables nvar, and I am also looking at error.cv, which is my cross validation error. I am looking at this with the CV. I am looking at number of variables on the x-axis and the error.cv on the y-axis. So let me see what this RFCV came out. So the RFCV has actually come out with all these things. The predicted 4, the predicted 7. So we are talking about predicted. If you are looking at CV, the number of variables that are coming out 14, 7, 4, 1. That is coming as a part of. So these are the 4 different sets of variables that have come out. And error.cv also has come out with 0.0833, 0.09, 0.18 and 0.42. This is how the error computation has typically come out. So I want to plot this versus this. So that is what I tried, right? I'm trying to plot, otherwise let me say cv$n.var cv$error.cv. So let me take those two things. I'll take the plot cv$n.var, and I'm also looking at cv$error.cv. These two things I should get a graph of this. Yeah. So we have, and probably I'll set this equal to line, right? Rather than we will say type equal to L. So this is how the errors are coming out, let's say, which means after 7 we see that there is a flattening out of the error that is happening. When there are only one variable, the error is looking much higher. When 4 variables are considered, it has gradually drastically reduced. For 7 it has fallen even more, but after 7 to 14 it has almost stabled out. That is what is being given as a part of my cross validation model. So we are plotting the cross validation error versus the number of predictors. So we, as the number of predictors error is increasing, the cross validation error is actually falling. But after 7 variables, I could see that the cross validation error has more or less flattened out, which means the 7 variables are more or less very less important in the process. Only the 7 predictors are more and more important in the entire process. Now this is what we could get even by looking at the variable importance that is coming through the fit. I can very well look at the variable importance by using the var imp plot function. Var imp plot, which is the plot of variable importance. So I could do this with fit or probably fit 4, fit 5, everything, which is clearly giving me an indication that maximum length. So again, there are two ways in which it has computed the process. One is based on the mean decrease accuracy. If this is removed, if this particular variable is removed, by how much extent is the accuracy falling? So if I remove this particular variable from the model, maximum length aspect ratio, I see that the accuracy is falling by approximately 60, which means it's a very important variable in the process. Similarly, the distance circularity, if I am removing this, probably the accuracy is falling by 40. Maximum length rectangularity, scaled variance, minor axis. So these are the ones that are more and more important, but probably skewness of the minor axis, it looks like the importance is much lesser. So is the case with scaled radius gyration, the radius ratio, which are looking like very minutely important kind of variables. By going with the mean decrease in accuracy mechanism, even the other mechanism that is being tried for plotting the importance of the variables is the mean decrease in the Gini value. Here we could see that maximum length, even in this mechanism, the maximum length aspect ratio comes out to be the topmost important one, whereas scaled variance minor axis, which has come in the 4th place here, came into the 2nd place out here. Elongatedness, which is in the 6th place here, came to the 3rd place here. So depending on the kind of method that we are using, the rankings of the various variables are lying in some cases, but overall if you see also, the top 5 variables or the top 6 variables are just interchanging the positions, but they are not moving out completely from one method to the other, which means we can, on a broad scale, we can very well assess which variables are important and which variables are of least important. Overall, I could clearly see that the maximum length aspect ratio definitely is a very important parameter, because in both the cases it is coming out to be in the top 1 position itself. So we are getting the variable importance, and I could now clearly see the proportion, right? I can very well look at the margin for the fitment. So which is nothing but the proportion of votes for the correct class, how many votes that the correct class has received, minus maximum proportion of votes for the other classes. So we are looking at what is the accuracy with respect to, so let's say if a particular vehicle needs to belong to the class bus, I am looking at how many votes came per bus. Out of the 1,000 trees we are talking of, how many of the, what proportion of the votes came per bus? If it is a bus, let's say 600 came per bus. So this is 0.6 minus the maximum proportion of the votes per the other class. Probably the next class is SAP, and we got 30% of the votes per SAP for the same vehicle. So the correct classification is 60%. The maximum of the wrong is 30%. So the margin is coming out to be 0.3. Now this is what is typically being shown as a part of the margin of fitment. So if the margin is very positive, means there is a high amount of correct classification, whereas if the margin is negative, it indicates that there is very high amount of wrong classifications or the error in the classification. So that's one more kind of a graph that I can very well look at. I'm looking at the plot of margin associated with the fitted values. The margin associated with the fitted values are typically showing as the, now you could see where when the tree size is much lesser, right, you could clearly see out here when the tree size is much lesser, we are seeing that things are very negative. But as the things are more and more increasing, right, as the values are more and more increasing, you could see that the x is increasing, which is the difference between the maximum proportion. It has touched almost the 1 mark, which is an indication that the classification is very accurate. Very minor misclassification rate that is coming up, and that's a clear indication of the accuracy of the model. So I can very well look at the plot of the margins also to assess whether the model is very accurate, whether the classification is done properly, or there is some kind of erroneous classification in the overall process. Then once the model is there ready for me, I can very well go ahead in terms of using the fitted model on the test sample. Now, if I have to use the fitted model on the test sample also, here also I am using, see, I can use the fitted model on the test sample. So again I am using the random forest function itself. The only thing now is, if I want a different fit, then I can create a new fitted model altogether. Right? If I want a new fit, I can create a fitted model altogether. But if I want to try out this model itself, now if I want to use this model on the fitted, probably I can very well use the pred. Right here it has already done the fitment. The model is already predicted. So that is for the training data. Now I want to use on the testing data. So I want to do the predict and use the fit, and I want to give the testing data as the input. Test data without, with all the rows and without the 15th column. So there is a prediction that is being performed. So if I look at the pred, it gives me that each of the observations, it has actually classified whether they belong to bus or sub or van. Now based on this, I can very well look at the table of actuals versus the predicted. So I can very well take the table. The predicted is the pred, whereas the actual is coming out from the test data and the 15th column of the test data. So this is what is giving me a table. I could see that 68 predictions are correct here, 55 predictions are correct here, and 53 predictions are correct here. So overall here it is 108 plus 68, 176 are correctly classified out of overall 176 plus 9, 185 and 190. Right, 73 plus 56, 129, 129 plus 61, 190. Out of 190, I could see that 176 of them are correctly predicted using this particular model, which is resulting in approximately 92.63% accuracy resulting in an error rate of around 7.5%. But probably if I had really worked out with some other M tries, when I'm saying some other M tries here, the M tries could be set to 4, 5, etc. If I'm working with some other set of variables, some other subset of the variables, there is a good chance that the accuracy of classification could be much higher on the testing data. But this particular model for this data has given me an accuracy of around 92.63%. Now I should really look at whether any other models like decision trees or some other kind of model can give me an accuracy which is much higher than this. If they are giving, I would be preferring those models. If they are giving me a lesser amount of accuracy, then I could still prefer using this model for my future prediction purpose, because the accuracy is much better in this kind of a model where it is able to classify the data more and more appropriately into their correct classes. So that's how I can use the classification random forest example, random forest model, from the random forest package using the random forest function to do the classification of multi-categorical kind of a data. Right? Now, next move on to the next algorithm for the classification process itself, which we will be calling it as conditional inference classical random forest. So the classification itself, but this would go with a conditional inference kind of a model, which is coming from the party package which we have installed earlier for various decision trees and various other processes. This would use a function called cforest. So let's try that out. Let's load the party function. Let's load the party package. Alright. Now I have to use the cforest function. Let's see what goes as a part of this function. It's an implementation of the random forest, and this also implements the bagging ensemble algorithms. Bagging is nothing but bootstrapping aggregation. So it is utilizing the conditional inference trees as the base learners in the whole process, and the random forest implementation is typically done. If you look at some of the inputs that it goes with, it requires a formula. So we are anyhow using the same data for creating this random forest as well. Right, we are looking at the cforest, where we are looking at the formula, which is the response variable tilde, a set of all the explanatory variables. The data here looks like it has to come in the form of a list, but it's a data frame, because data frame is a kind of specialized version of a list. So I am giving the data as a data frame containing the variables in the model. So I can give the name of the data out here. The subsets, because I am not working too much on the subsets, I can ignore all those things. But the controls is something I can very well set. Right, I can very well go with cforest controls. So within this I can use the cforest unbiased or cforest classical. So by default it's a cforest unbiased that is going to come out with. I can set the controls from the cforest control. Looking at the cforest control, I can very well give the test statistic, which is the type of test to be applied, right? How the computation is to be done, the minimum criteria, if I have any, I can specify that minimum criteria. Basically I would be using the number of trees, or if I want the M try, I can give the M try. So these are some of the controls that I can very well set. for this tree level out here. I can set all these kind of controls depending on the requirement, and rest all I don't think I need to give any of them. And if I require the proximity, I can very well set the proximity associated with it. So that is what is this model all about. So you could see here as a part of the PPT the control parameter wherein I can set the number of trees that can be grown in each iteration, whereas the default is around 500. So I can really see if I can increase this number of trees to 1000 etc., which come from the control parameters. And apart from that, okay, Z is my response variable. The response variable here is a multi-category classification variable, whereas the data is the data frame containing all the various attributes with which I want to build the random forest. So we'll get started with the process. I'm loading the party package, which is already done. Okay, towards the end, we will look at the performance. Right, this I could have done even for the earlier version of random forest also. The carrot package actually gives me different kinds of performance evaluations, especially the computation of the kappa, which is another sophisticated version of measure of accuracy of the model. So I really want to look at few advanced versions of, rather than just looking at the confusion matrix, and based on that talking about correctly classified versus wrongly classified, we can also take more and more advanced performance measures like kappa. So because of that reason, I want to use the carrot package as well, so that I'll get some sophisticated performance metrics for the random forests after the classification is typically done. So we are getting the necessary data. We have already loaded the data. We'll go ahead with that data itself. Preliminary checks are being performed because we are reusing the same data that we have used for the classification random forest from the random forest package. Split the data into training set as well as testing set. That is also taken care of. Now we can estimate the random forest using the training sample and the C forest function. Now we are in a position to very well use the C forest function and go ahead in terms of building the model. Okay, so I'll call this as fit. From the fit I can use C forest function. From the package party I can use the C forest function, where my dependent variable is class tilde dot. The data which I am using is train data, which is my training data. The controls, whenever we want to go with the unbiased, the default implementation is unbiased itself. So we will say C controls. Let me just open that. Okay, looks like I have deleted that. So let me recall the previous one. Okay, so this is what I have to give. The C controls, let them be here so that we can specify that. Now I'll call again the fit C forest, wherein the class is my dependent variable tilde dot. The data is coming from the train data. Then I have controls. Let me set the controls based on C forest unbiased. So this is the set of controls I want to take, and within that these are all the ones that are default. Instead of entry equal to 500, let me set the entry equal to 1000, and mtry by default it is 5. I can very well set with 3 or 4. Right, let me say mtry equal to 4. So this is what I want to set as a part of this controls for this particular model, and based on that I'm going ahead in terms of fitting this model. Now I have the flexibility with respect to the controls. I can change the number of trees, right? The flexibility that I have for this model is: one, I can change the number of trees; two, I can try changing the M try. So based on that, different models can be fitted. I can really look at the accuracy of all the models. Now here we have a way of assessing. We have something called C forest stats. Look at the C forest stats. Okay, you read you need carrot package for that. So let me install the carrot package. Okay, install.packages. Library carrot. All right. Now I can see C for a stat, which is a conditional inference for X. I can get the statistics for it, which is I can get the C for a stats of X. These are the different internal functions that are supported, right? The C for a stats I can very well get. So once you type in the C for a stats for this particular fitted model, you will see C for a stats. I look at per fit. Now here I am getting, if I am going with the accuracy in the normal way, right, looking at the misclassifications after plotting the confusion matrix, if I am looking at just the misclassifications, the accuracy is coming out to 91.21%, but kappa is a much more sophisticated measure of accuracy, more reliable measure of accuracy of the model, which is resulting in 86.83%. So that is a much more, we have already defined kappa and various other performance measures as a part of one of our sessions on advanced performance measures. So you can refer to that particular video on advanced performance measures, where we have discussed how the kappa gets computed and how you can really use kappa as a measure of accuracy of the model. So in this case, the kappa is showing 86.83%. So that is the real accuracy of the model when we are going with the training data. When I am applying this model on the training data, so we are looking at not just the confusion matrix based accuracy, we are also looking at the kappa statistic, based on which we can assess the reliability of the true accuracy of the model. Now once this is done, I can very well go ahead in terms of I can very well go ahead in terms of doing the importance of each of the variables, right? That is what I can accomplish using the var imp function. So I can very well take var imp of fit. The var imp of fit is actually giving the importance of each of the variables. Let's see what is the importance it has assigned to each of the variables. Probably it has assigned it in the serial order. So this is where I can think of sorting, sort var imp of fit. Okay, this sorting is in the ascending order. So let me do a reversal of the sort, which gives me the sorting in a descending order. So here I could very well see that elongatedness is the most important variable, the contribution being around 13.6%. Then comes the maximum length aspect ratio with a 9.8% importance, scatter ratio with 7.94, scaled variance minor axis with 7.4, distance circularity with 6.8, and so on. And probably skewness minor axis is hardly contributing with 0.1%, and scaled radius gyration is giving contributing around 1.4%. So you can very well assess those variables which are very important versus those variables which did not play any kind of a role in terms of the building of the model. So we can very well understand what are the variables that are important and what are the variables that are unimportant in the process. Now we can very well go ahead in terms of the prediction part. Right now that all these things are taken care of, now we can very well go with the prediction part. The prediction part also I can fit. So let me go with pred, using where I am using the predict function. I am using the fitted model, and the new data for me in this case is the test data. That's the test data which I am working with, and I want to get the response out here, but the test data I will omit the 15th column, right? So that is what I'll give as the new data for this, and the type I am setting it as response so that I'll get the classification of this. So there is a prediction that is being performed. Now when you look at the pred, we get that each one of them is either predicted into a bus or a van or a Saab. Now based on this I can very well look at the classification or the confusion kind of an error. So first thing, let me look at the table where I am using the pred, and the actual values are coming from the test data from the 15th column. So based on that I get a table. I see that 68 of them are correctly classified as bus, 47 of them are correctly classified as Saab, and 51 of them are correctly classified as van. Okay, so these are the predicted values, these are the actuals. So actuals, we have 71 buses, 68 of them are correctly classified, 3 of them are being classified as van. Saab, we have 66 Saabs. Out of that, 47 have been correctly classified as Saab, 8 of them have been wrongly classified as bus, and 11 of them have been wrongly classified as van. Overall, we had 53 vans, 51 of them are correctly classified and 2 of them are classified as bus. So going with the accuracy of the model, so this is 98 plus 68, resulting in 166 out of 190 being correctly classified, giving me an accuracy rate of only 87.36% using this model. Whereas when we have used our earlier model, we have got an accuracy rate of 92%. So that is where probably the random forest function from the random forest package has given us a much better prediction on the testing data for this particular model rather than rather than the conditional inference random forest, which has given us only an accuracy of 87.36% only. So again, it's nowhere guaranteed that this model will always give a lesser performance compared to the classification random forest model. So that's the reason you have to keep checking different kinds of models with different adjustable parameter values, with the final objective of wherever we are able to secure higher and higher levels of accuracy, that would be the most preferred one for the prediction purposes. This accuracy I may have to get it on my testing data so that I can very well use it as a base for predicting unknown values altogether, right? So that's how we can look at our second model, conditional inference classification random tree. The process is highlighted for you as a part of the PowerPoint slides, which you can very well refer to when you are getting into some kind of doubts or ambiguities in terms of the execution part, right? Now we can move on to our next model. The next model for multi-category classification is the classification random ferns. So now we would be using the random ferns instead of the random forests, where we can understand what the difference that has come out in the model out here. But yes, before this, if I type in the fit out here, it has clearly, for the earlier model, it has clearly said that 1000 trees have been created. These are the responses, and the number of observations that it has gone with is 444. And that is a part of the training data. Now if I talk about the print of this fit, again you will get the same information out here. But when you go with summary of this fit, you will get that it's a random forest of length 1. And so when you want to go with a plot of this fit, because it's an S4 object, it will not be I cannot create a plot on the fitted model. That's the reason we have gone with a few other aspects when we have used the conditional inference classification random forest. Now, when we are getting into the random ferns, I'm using a package called rferns, and the function that I'm using is also rferns. So let me install the package first. Then we are also loading this package. Right, we have loaded the package. We require the function called rferns. So let's see what this rferns function is doing. This function builds a random ferns model on any given training data. Straightforward. Random ferns model is typically built on the training data. And the input that it generally takes is, I can go with any of the different implementations. Here we are going with the formula based implementation. So we are looking at the formula, which means the dependent variable tilde the independent variable. Then we have the data, we are giving the data. But apart from that, I can specify the depth. The depth is talking about the depth of the ferns. So it can go right from 1 fern to 16 ferns. So it is basically the memory requirement scale to 2 to the power of 10. So if I am setting the depth as 5, then it is going for 2 to the power of 5, which is the 32 leaf nodes altogether. So that is where I have to specify the depth of the ferns, number of ferns that it has to create. So which is something which can control how many ferns have to be created for this purpose, just like how many trees have to be grown in case of random forests. Here we talk about how many ferns to be created. Again, if required, I can very well set the importance. So here we have different kinds of importance measures. By default, it is set to none. Right? If I want, I can very well bring in the importance factor as well. But here, I want to really come out with a few important things. Save error propagation. If you look at the save error propagation, should the out of the bag error approximation be calculated after each fern was created and saved? So I want the out of the bag error to be created after each fern is created and saved. So I can very well set it to true and report error every this many number of iterations. So if I'm setting, I'll get the OOB error approximation after every chunk. So every one entry, every 5 entries, every 10 entries, after every n number of ferns are created, I can get the error. So if I set it to 1, it means after every fern is created, I want a report of the OOB error. So those two things are very important for me. For every fern that is created, I can very well look at the out of the bag error that is coming up. So I think those are some of the important things that I am giving as an input for this particular model, and I can now get started with fitting of the model for the same data. Looking at the prerequisites for it, I think we have already taken care of. We have loaded the package because we are using the same data of vehicles. All these steps are already done. Now I am going ahead with fitting the model using the rferns. As I have said, I will set the save error propagation to true because I want to look at the OOB that is getting created for each of the ferns, and I really want to see what should be the minimum size of ferns that we have to create so that the overall OOB is the least possible, because otherwise there is no point in just increasing the number of ferns just for the sake of increasing in case I am not able to get any kind of an improvisation in my OOB.